Division by 3 in Python. I am new to Python, and while experimenting with operators, I came across this. Shouldn't the result be 2.333333333333333333 or maybe 2.3333333333333334? Why is it rounding the number in such a way? Also, with regard to floor division in Python 2.7, my results were So my observation is that floor division returns the integer quotient even in case of floating numbers, while normal division returned the decimal value. Is this true?
Take a look at this 0.300000000000004.com. Your language isn't broken, it's doing floating point math. Computers can only natively store integers, so they need some way of representing decimal numbers. This representation comes with some degree of inaccuracy. That's why, more often than not, 0.1 plus 0.2 not equal 0.3.
Shouldn't the result be 2.3333333333333333 or maybe 2.33333333333334? Why is it rounding the number in such a way? The key is the number is being rounded twice. The first rounding is part of the division operation, rounding the number to the nearest double precision floating point value. This is a binary operation, not a decimal one. The second rounding is part of converting the floating point number to a decimal representation for display. It is possible to represent the exact value of any binary fraction in decimal, but it is usually not desirable, as in most applications doing so will simply result in many digits of false precision. Python instead outputs the shortest decimal approximation that will round trip to the correct floating point value. We can better see what is going on by using the fraction and decimal types. Unlike converting directly to a string, converting a floating point number to a fraction or decimal will give the exact value. We can also use the fraction type to determine the error in our calculation. The conversion via type decimal shows us the exact value of the floating point number and demonstrates the many digits of false precision that typically result from exact conversion of a floating point value to decimal. The conversion to a fraction is also interesting. The denominator is 2,251,799,813,685,248, which is equivalent to 251. This makes perfect sense. A double precision floating point has 53 effective bits of mantissa, and we need 2 of those for the integral part of the result, leaving 51 for the fractional part. The error in our floating point calculation is 16,755,399,441,055,744, or 1/3 2 to 51. This error is less than half our precision step of 2 to 51, so the answer was indeed correctly rounded to a double precision floating point value.